So in this video, we're going to be graphing rational functions that have what's called removable discontinuities, okay? On the graph, it's going to just look like a hole, okay? When we graphed some piecewise functions back earlier in the year, there would be some times where there was a hole in the graph. And this is going to be the case here with these removable discontinuities. Now, the vertical asymptotes are also considered discontinuities, okay? In calculus, continuity is a huge concept that you're going to deal with. And a continuous function just means it goes forever, like a parabola is continuous. You never pick up your pencil or your pen when you're graphing that function, okay? Rational functions are going to have discontinuities, whether it's in the form of a vertical asymptote or in the form of a hole, okay? Now, these holes occur because of what happens when we simplify the given functions, okay? So remember, our first step when we're graphing rational functions is to simplify. So we can factor the numerators, the difference of squares, so x plus 1, x minus 1. Notice these x minus 1s cancel out, okay? If you didn't factor first, you might look at this and say, hey, we've got a vertical asymptote at x equals positive 1. But when we simplify, that x minus 1 cancels out. So this function is not going to have a vertical asymptote, okay? It's going to have a hole, or what we call a removable discontinuity, okay? So when we simplify this function, it ends up being just your basic linear function in slope-intercept form. So the y-intercept would be at positive 1, the slope would be positive 1. So when you graph this, it's going to look like a line with one exception. There's a removable discontinuity or a hole at x equals 1, okay? So we're going to have a line that goes through positive 1 with a slope of 1, but there's going to be a hole right here at x equals 1, okay? So I'll show that on the graph right now. So in this first example, remember we had a linear function f of x equals x plus 1 with a hole at positive 1. So just using our slope-intercept form, we're going to put our y-intercept there, okay? If we use our slope of positive 1, there's going to be a hole there, and then we can use our slope to find more points, okay? So the graph's going to look like this going down to the left, and it's going to look like this going up and to the right. So there's the graph of that function with a hole at 1, 2. So let's look at this second example here. We've got f of x equals x plus 2 over x squared minus x minus 6, okay? So again, first thing we want to do is factor, and our denominator looks like this, x plus 2, x minus 3, okay? Now again, if you weren't thinking about removable discontinuities, you would think, well, I've got two vertical asymptotes, okay? Here, one at negative 2, and this one at positive 3. But in the simplification process, these x plus 2's cancel out. So my actual rational function that I'm going to be graphing is 1 over x minus 3 with a hole at negative 2. Okay, so because that canceled out, this will be a rational function with a hole at x equals negative 2. Okay, so because we have a rational function, we have to go through the process of graphing rational functions, determining the asymptotes, determining behavior approaching the vertical asymptote, and determining end behavior. Okay, so first thing I want to do, we've got a vertical asymptote, intercepts, x-intercept none, y-intercept at negative 1/3, okay? Can't have an x-intercept because the numerator is 1, okay? So this could never be 0, okay? Y-intercept at y equals negative 1/3, well, if you replace x with 0, then you're left with 1 over negative 3, which is negative 1/3, okay? Now let's go to the vertical asymptote. It's going to be at x equals 3, okay? Remember how to find the horizontal asymptote. Degree of the numerator is 0. Degree of the denominator is 1. So the degree of the denominator is greater, so that means we've got a horizontal asymptote at y equals 0. Okay, so now we want to determine behavior as we approach 3 from the left and 3 from the right. Okay, so coming from the left, I'm not going to do as many points this time as I did on the previous videos when we were just learning how to graph rational functions. So I'm just going to do 2 on each side this time. So I'm going to start with 2. We're just a little bit to the left of 3 here. And when I plug 2 into my rational function here, I get a negative 1. Okay? Now I'm going to go really close to this 3. I'm going to use 2.9 here coming from the left. So when I plug that in, I get negative 10. So you can see we're staying negative, but the magnitude of that value is getting larger. Okay? So what we say as x approaches 3 from the left, then y is going to approach negative infinity. Okay? So now we want to come at this 3 from the right side, so we're going to start with 4. Plug that into the function, we get a positive 1. And then let's plug in 3.1. We want to get really close to this 3 just to see what's happening. And when we plug in 3.1, we get a positive 10. So you can see the closer we get to 3, from 4 to 3.1, our numbers are getting larger, okay? So we say that's gonna, as we approach 3 from the right, then y is gonna keep getting bigger, so it's approaching positive infinity, okay? And then in behavior, let's plug in a really large negative number here, and that's gonna give us negative 0.001. So as x approaches negative infinity, y will approach this horizontal asymptote from below, okay? Let's plug in a really good positive number. That's also gonna give us 0.001. So that's gonna say as x approaches positive infinity, y will approach 0 from above, okay? So let's graph all that with a focus on where this hole is gonna be at x equals -2. So graphing number 2 here, I've already plotted the horizontal asymptote at y equals 0, the vertical asymptote at x equals 3, and the y-intercept at -1/3, okay? So we know just from some of the points we plotted, we had a 2, -1 point right here, okay? And we know as we approach this vertical asymptote from the left, we're gonna be going down to negative infinity, okay? All right, now as we go to the left, remember we were, as x approached negative infinity, y was approaching 0 from below, okay? So normally we would just take this graph all the way to the left here, but we know we've got a hole here at -2, so we need to put that in. It's gonna be really close to the axis there. So I'm gonna go to that, and then from there I'm gonna continue towards 0 from the bottom side, okay? So this graph would be just like the graph of the function 1 over x minus 3, but because we had simplified before we got to that expression, we've got to put the hole in there, okay? On the right side here, to the right of the vertical asymptote, we had a point 4, 1, okay? We knew as we were approaching the asymptote, we were going towards positive infinity, and to the right, we knew we were going towards 0 from above, okay? So there's the graph of the function f of x equals x plus 2 over x squared minus x minus 6, with a vertical asymptote at 3 and a hole at -2.